delighted to be here today, and so thanks to the organizers for giving me the opportunity to address you this morning. So when they've been, I think, given a very broad mandate talking to you about multimodality molecular imaging and its potential applications in personalized medicine. And this is, I think, sufficiently broad topic that I can probably talk about this the whole morning. So this is going to be one of these talks where we have sections we go a little into detail, and other sections we sort of skip over. So hoping to learn some time for questions if anything is missing from anybody's expectations. So just have, I think, large number of slides. So whenever I go over my time, so please stop me, okay? All right, very good. So let's start this talk about there's a place where I live. So Geneva is famous for this jet d'eau, the famous water fountain, and summer, nice summer nights also. So enjoying. We didn't have very good summer this year. I mean, obviously because of the pandemic situation. But anyway, I mean, it's a very nice place to raise a family. And this is on the left side of the place where I work. So Geneva University Hospital, and the medical school is just located in front of it. And my research group is active in a number of areas that are summarized here. And in these talks, I'm going to basically address the first three topics: multimodality imaging, quantitative imaging using hybrid technologies, including PET-CT, so positional emission tomography combined with X-ray CT, and magnetic resonance imaging. And if I have the time, so I'll just guide you through some of the ongoing developments in the area of deep learning guided medical image analysis. So this is not really an outline, but kind of a list of topics I'm going to address today. I'll go through the advances in multimodality imaging. I guess the audience is quite heterogeneous, so with some of you who did not really have experience or expertise in this area, so it's going to be kind of introductory talk. And then I will go through the software versus hardware integration of medical imaging technologies, going through from PET-CT to PET-MR, and then the last part, as I mentioned it. So if you have the time, so I'll guide you through some of the developments where we see really an application of AI-based solutions in the area of quantitative imaging, and then I'll summarize this talk and give some possible scenarios for future developments in the near future. So just to give you a very brief overview of the technologies I'm going to describe today. So this is how we were taught when I was students. We were taught that there are basically different classes of medical imaging technologies. What you see on the left side here, if you see the mouse, is anatomical or structural imaging modalities, where you have X-ray, CT, ultrasound, magnetic resonance imaging. So this is basically radiology if you want to see the structure and the anatomy, if you're interested to see the physiology, if you're interested really to explore the biology of different diseases. So you need to use one of those molecular imaging technologies that I'm going to talk about today. And basically optical imaging, which is less used actually in the clinic, but used in preclinical imaging using small animals like mice and rats. But the two technologies that we use in the clinic are basically those that you see here: positron emission tomography and single photon emission compute tomography. So the idea is that with integrating imaging modalities, so we exploit, for instance, the high spatial resolution of MRI and X-ray CT that happen to have a very high spatial resolution compared to molecular imaging techniques. And the advantage of the latter is that they have a very high sensitivity. So basically, I mean, comparing the two, we're in the range of picomolar sensitivity for positron emission tomography compared to the millimolar sensitivity with X-ray CT, and probably with the range of factor of 10 for MR. So the idea is to combine the two technologies to address or to solve basic and clinical research questions, taking advantage of basically, I mean, the pros of both imaging modalities when integrated into a single system. So we have witnessed it also during the last decade, major developments and evolution of the technologies, and the opinion leaders predict that planar imaging is probably going to disappear. So what you see here, two-dimensional projection imaging, is probably going to leave the space for three-dimensional imaging, so where you see the 3D information X, Y, and Z, so it could be CT or nuclear medicine techniques. And then when we add the time information, basically the fourth dimension, we can, through gating the data, we can basically explore the trace of kinetics for 40 PETs, using 40 PETs, or capture the motion of moving organs such as the heart or any moving lesion located in the thorax, in the upper abdomen. And obviously, when we use hybrid imaging technologies that combine PET and CT, we can basically get the information that we need for the fifth dimension, and then we can increase the dimensionality of the data set. So Geneva is very well known actually for development of software for medical imaging applications. So including this platform called Osiris that runs on Mac. And then it's funny actually to see colleagues, radiologists during the coffee breaks in the morning, so looking to medical images on their iPhones, iPads, whatsoever. So it's really fun to see how the developments are getting to the point they're getting to these days. So some history here. So this is the timeline of molecular imaging. So starting obviously, so what I'm missing here, so for medical imaging at large is the discovery of the X-rays by Professor Groningen, a Nobel laureate in physics, 1896. And then the history of molecular imaging and nuclear medicine started with the discovery of radioactivity by Becquerel, Pierre and Marie Curie. And then you see a number of pioneers here that contributed basically to the development of these technologies. So starting from Lawrence, who developed the first cyclotron with funding that he got from the Rockefeller Foundation in the States. Anderson, so major discovery, he discovered the positron, another Nobel laureate in physics. Without the positron, there would be no positron emission tomography. And then you see the Hevesi, famous Hungarian biochemist, another Nobel laureate in biochemistry. He basically developed the tracer principle that we use for molecular imaging. And you see a number of other pioneers who contributed actually in developing instrumentation that is used nowadays. What's important here to notice is that the first papers actually on combining PET with MRI were published by Hammer Christensen from the US. So really before the advent of PET-CT and even SPECT-CT, as we will see later during this talk. So some of the history again, so this is the next slide on the history. So the first PET's devices, I mean, the first applications of position emission tracers dates to the basically the 50s in the Massachusetts hospital where Brunel, Snyder, Sweden, and their colleagues actually put into evidence brain tumor, as you can see from this illustration here, using a very simple apparatus consisting of sodium iodide crystal and a number of PMTs. And then the technology was developed later. So with the development of the first PET scanners in the 70s operating in tomographic mode, and obviously the spatial resolution was not very good, as you can see from this first FDG PET image produced by the group of Professor Abbas Alavi from the UPenn in Philadelphia. And according to him, so when he was really proud showing his first image actually to his colleagues, radiologists, that were at that time extremely excited about the developments going on in MRI. And obviously they were not really excited about the quality of the image, which was very blurred, very low spatial resolution. And then they told him, hey, Abbas, this looks like a painting. And the advantage actually with of PETs at that time is that we can't quantify. So the glucose metabolism, blood flow, and different biological phenomena, something that you cannot really do with MR. So this is one of the major advantages of molecular imaging, is that it's quantitative, as we will discuss later on during this presentation. And obviously, so for PETs, you need a cyclotron, and you need, and then you can get access to a pretty large number of molecular imaging probes that you can inject to your patients actually to target different molecular pathways. And these are some of the tracers that have been developed, and many of them are applied in the clinic. And obviously, many of them didn't get through and stayed just simply at the stage of scientific publications. So just to show you basically the evolution of PET in terms of image quality and spatial resolution, you see that with the first image, as I mentioned, is really suboptimal image quality and spatial resolution. So with the voxel size close to 1 centimeter in the 70s, and then you see basically the evolution and the improvement in image quality, which basically follow the developments in instrumentation. So we have witnessed the developments and the use of new facet scintillator crystals with high spatial resolution. Many of the scanner manufacturers included the axial field of view, so basically to improve the sensitivity. Major developments in electronics actually that allow to follow very high count rate. And more importantly, so the incorporation of statistical iterative reconstruction techniques with accurate system modeling that allow actually to recover the spatial resolution, and this enhanced substantially the image quality, and also the improvements in signal to noise ratio achieved with the time of flight introduction of this technology in the clinic. So back to the basics. So for those of you who never heard about PETs, positron emission tomography is a medical imaging technique which is used in the clinic to scan patients. It has a pretty large number of applications. And obviously, so we inject positron emission tracers to the patients. And once the positron emission tracers, it goes to the cells that we're interested actually to study the organs that we're interested in. So the positron is emitted, so it's going to travel certain distance depending on the maximum positron range, and then it interacts with the electrons that we have in the biological tissues, and this gives rise to positron electron annihilation and the emission of two back-to-back annihilation photons. And then we've got a number of scintillation crystals arranged in cylindrical geometry that are going to collect the different lines of responses that we put in what we call a sinogram that you see here. And then the simple image reconstruction techniques basically filter the projections and then back projects the filtered projection into the image space to get to the reconstructed image from the measured projections, and obviously in the clinic. So more advanced iterative reconstruction techniques are being used, and these techniques basically provide excellent image quality suitable for the clinic. So in terms of instrumentation, so most of the clinical scanners are based on this partial ring geometry and a number of scintillation crystals, a bunch of crystals arranged in intercylindrical geometry, and most of the scanner manufacturers, they manufacture these scanners that can be used actually for whole body scanning, meaning that you've got a limited axial field of view between 16 and 25 to 26 centimeters, and then to cover the axial field of view, which is desired. So basically 1 meter, 1 meter point 120 centimeters, we basically need to move the patients and then concatenate all the bed positions to basically have a three-dimensional volume of the whole area that is of interest to the clinicians. And then we've got some dedicated systems dedicated, specific for various organs. And we've got some systems dedicated for brain imaging, for breast imaging with a very high spatial resolution, some systems dedicated for prostate, and some of them also dedicated for biomedical research applications. Imaging basically rodents, rats, and mice, and these are devices with submillimetric spatial resolution. And there is a new trend actually, so called total body PET, which is a very high research topic right now. So researchers from UC Davis, from UPenn, from a number of facilities, so collaborating with some commercial companies, have devised around 2 meters long axial field of view PET system that can be used actually to to scan a patient in fraction of the time that is required for whole body PET imaging using conventional technologies. Just to show you some of the systems that have been designed for brain imaging, you see, so this is the high resolution research tomography designed by Siemens. 15 or 20 years ago. So I think it was designed somewhere than that, probably it's in the 90s, with a spatial resolution of 2.4 millimeters. And then you've got different design trends, including this HR from Japan. So very nice design concept, because you need to be able to scan the subjects in different postures. The subject could be lying, could be sitting, or could be simply lying on a bed. And then this device can be used actually for neuroimaging experiments, where the interest is basically to explore regions in the brain that are associated with some psychological issues. So for instance, looking at areas in the brain that are activated by the language and by different issues. So just to have an idea of the spatial resolution that you get, so as a physicist, we usually scan this type of phantoms that we basically fill with the radioactivity, and then we put them in different scanners to have a sense of the spatial resolution that we expect that we can get. And you see that this is basically what we expect to get, the actual, and this is give you a sense of the spatial resolution that is achieved by those scanners. This is actually a human subject, so that was scanned twice with a single injection. So scanned on the commercial system, the whole body system, the biograph basically, and the high resolution research tomograph dedicated for the brain. And I guess you can appreciate the improvements in spatial resolution that is achieved with this system. These are other scanners that have been developed more recently. So you see that you can, this is the HUD system developed by Japanese scientists. You can simply, put a bunch of detectors just around the head. And there is an interest to develop some systems that enable actually you to scan the patients or the normal subjects, which are simply walking or doing their exercise whatsoever. So this is very, very interesting and very high, I think, research topic that is being investigated by a number of groups. Positron emission mammography is also of a special interest. Basically because of the limitations in terms of spatial resolution that can be achieved with the systems that are used actually in the clinic. So these are systems dedicated for breast imaging. They give you very high spatial resolution. So you can see actually this Lorenzo phantom, excellent spatial resolution, close to 1.5, 1.6 millimeters. And the blurred images that are obtained with the dedicated body system. And this is a clinical study actually, so comparing PETs, PEM and MRI for a lady having two IDC lesions that are not seen by the mammography, missed by mammography. You see them very clearly on the MR, but we also see them on the PEM scan. And these lesions were obviously confirmed by the pathology. The advantage of PEM is that the interpretation time is much less compared to the time spent by the radiologist within the MR. So this is the new trend I just mentioned. So the total body PETs pushed actually by scientists from the UC Davis, Simon Churi, Ramsey Badawi, and their colleagues in collaboration with United Imaging in Shanghai. So they came up with not really a new idea, but they managed to get, if I recall, was around 16 million funding from the NIH in the United States to design this very nice system. And you can see, so this is Ramsey Badawi actually look into the system, very excited obviously about this developments, and the number of papers are now in the literature, so really very interesting. The other development which is worth mentioning here is small animal imaging, so for dynamic applications, or actually there are pretty large number of PET systems, animal mice and rats, and basically using different molecular imaging probes to explore different molecular pathways. And some of the interesting developments that you can see here is basically the rat cap for use applications. So things that really understand the ones in his living environment without the need of anesthesia, such that that's around the hand of the rat and can achieve his own environment. Another design trend pushed by a group from Manchester in Germany is basically tracking devices, in hospitals and then able to recover basically the acquired events and then do a reconstruction, so taking into account the position of the hemorrhagic or small box. Now coming to the topic for multimodality imaging, so obviously X-ray and MR, so historically belongs to radiology, PET and SPECT belong to nuclear medicine. So the idea basically is to fuse or to align the images to be able to make a diagnosis, to plan a treatment, or to monitor the response to therapy. And actually the idea is not new. I mean, the 70s and the idea 80s, so the clinicians, the radiologists, nuclear medicine physicians expressed the interest to be able to have the access to the tools to be able to co-register or to align the images. And they were doing this manually right at that time, even if for the brain. So the concept is not really straightforward, but doable, in the sense that the brain is a rigid organ which is attached to the skull base. So it's quite easy to perform a rigid body registration and achieve submillimetric registration accuracy. So this is one of the techniques actually used. So you use actually the reference image could be the MR or the CT, and the floating image is basically the low resolution nuclear medicine image. You apply some initial parameters to transform the image, and then the process is iterative, and then once you reach convergence, so you basically assume that the two images are aligned. And then, as I mentioned, so we can achieve very good alignment with techniques used for the brain, especially for tracers like FDG that distribute quite uniformly within the brain, and we achieve millimetric spatial resolution accuracy. And this is the de facto standard technique used in the clinic. So we use it actually in the clinical routine, especially for epileptic patients with the SPECT technologies, where we scan the epileptic patients twice, so during and between two crises, and then we align the two images, and then we subtract them to put into evidence the epileptic foci here, and then we line this with the MR to guide the neurosurgeon actually, so that they can resect the lesions in an efficient way. So this type of techniques do not work in other areas of the body, like in the upper abdomen or in the thorax, because we've got this physiological respiratory motion, and you've got different breathing patterns between the PET and CT images. Obviously, so the technologies used nowadays of CT scans can be acquired in a few seconds, and the PET scan is still acquired in a couple of minutes or 3 minutes, so depending on the protocols used. And obviously, you've got different breathing patterns and some kind of misalignment between the scans. But some groups actually, so including this work from, I think I got this slide from Piotr Slamka, from CEDARS, and with actually teaching the patients how to breathe and using some dedicated breathing protocols, we can achieve very good alignment accuracy. And for this type of techniques, obviously we don't use rigid registration anymore, so we use non-rigid or deformable image registration, where we need to estimate the motion fields on a voxel by voxel basis. So I would like to use this slide actually to illustrate the concepts. So this is a nice slide from Jake Van Dyke, who is a medical physicist, well-known Canadian medical physicist. And he has one of his students actually was working in the field of image registration. So he gave him his own photograph and the photograph of the baboon here, and asked him to use this thin plate spline image warping technique to align the two images. So these are some of the reference points here, and you see the outcome. So this is Jake deformed to match the photograph of the baboon, and you see that it works quite well. So this is another nice illustration from Lay from Stanford, trying to actually to change or to transform the image of Arnold Schwarzenegger to match the photograph of this singer. Always forget her name for some reason. So, and you see that it really works quite well, and you can obviously imagine that those techniques are extremely powerful and can be used in the clinic. So in the clinic, it's not obvious to use this type of techniques, especially in regions below the neck, for different reasons that I mentioned before. But what's important here is that I think there is a misconception in the way the history of multimodality imaging is reported, because many scientists claim that hybrid imaging started with PET-CT or even SPECT-CT, which is not true. If you look to the early references, actually published in the 50s, 60s by Minor, Cole, Anger, Sands, and Tuthill Beringer. So all of them expressed actually an interest to design a system that combines emission and transmission imaging in a single apparatus, a single gantry. But the first one who managed to do this is Professor Bruce Hasegawa from UCSF, who passed away 12 years ago. So he managed to get a CT scanner from GE, kind of donation, and then he modified the system using hyperpure germanium semiconductors, which have a very high energy resolution, so to just enough actually to discriminate between the energies of the X-ray beam and the 140 kV of technetium. And they scanned so few patients. This is one of them, having a neuroblastoma, so with the focal uptake here, obviously, so well aligned with the CT, so to do mapping and to be able to say exactly where the lesion is located using the CT as reference. So the kind of same concept has been also adapted for vets. The idea originated here at Geneva University Hospital by a physicist called David Townsend, who didn't manage to get the funding here, and so he moved to the States and got funded by the NIH to design this system, which combined an X-ray CT here that you see in the front with the positron emission tomography system in the back, and with a distance of about 80 centimeters, at least in the first prototype. So basically the idea is to get the scout scan, define the axial field of view, and then start basically the spiral CT by rotating the X-ray tube and the detectors on the opposite side, so acquire the spiral CT and then push the patient towards the PET detectors in the back here, and then fuse the PET and CT images and present those to the MDs for clinical interpretation. So one of the issues actually with when this technology was introduced, it is in the increase in the radiation dose. According to some protocols, so some institutions, including ours, by the way, so we use a low-dose scan for attenuation correction and mapping, and then this is followed by PETs, and then we do a diagnostic CT scan with contrast enhancement at the end. So summing up the radiation dose, and obviously for the PETs you inject FDG, so we, 5 or 6 millisieverts from the injection are between 5 to 10 millicuries of FDG, and summing up all these the contributions in terms of radiation dose from these different examinations, so it might end up with a pretty large effective dose to the patient. And this raised some concerns in the literature, so basically driven by people who are against the use of radiation in power plants, and but also in medical imaging. You see that the word CT radiation dose was cited more than 2,000 times in the English language media in 2010. And this has some applications, obviously, on industry, because the war was basically between the different scanner manufacturers to increase the number of detector rows. Toshiba so built CT scanners with more than 320 slices per revolution, and this war came to an end and to start another war, which is good for the patients. It's called the dose war, and nicely actually explain it from a conceptual basis in this debate between Nahas and Dr. Habib. So the idea is that basically, so that the war shifted between the number of slices to a decrease in the radiation dose, and this is obviously for the benefit of the patients. And one of the issues, one of the things that came back or was revived is the use of iterative reconstruction techniques in X-ray CT. And you see here for the same patients or the same raw data, the conventional reconstructions produce extremely noisy images, very low image quality, into very excellent, I would say, image quality achieved by iterative reconstructions with substantial saving in terms of radiation dose to the patient. And the same technology is so combining PET and CT is actually being used also for a small animal imaging, and this is one of the systems which were available a few years ago, and that is used in our institution. So a system basically equipped with the three modalities: X-ray, CT, PETs, and SPECT. So combining PET with the CT is kind of straightforward and I would say obvious, but combining PET with MR is more challenging, and obviously MRI is a multi-parametric imaging modality by nature, owing to the different contrasts that can be generated by the different sequences that can be used in the clinic. And combining this with multi-tracer imaging using PET is going to give you, a substantial amount of information that can be extremely useful in the clinic. So three different design concepts have emerged. The first one is basically a la PET CT, the same as PET CT, putting the two systems in tandem, docked way. The second is using a PET insert, especially for preclinical imaging, small animal imaging, inserting this into MR. And the third is a fully integrated system. Just to show you the systems that have been designed very quickly. So this is the system used in Zurich for a number of years. It's a Modality system with the patient transfer tabletop to take the patient from the PET CT scanner to a nearby MRI scanner. So again, with tabletop, patient transfer tabletop that enables actually to put with the two images into the same coordinates and into the same spatial coordinates. So different design trends have emerged, and these are the systems that are available today. The Philips system that we have been using in our facility, combined with 3 Tesla MRI with the time of flight system, so 3 meters distance between the two subsystems. Basically starts with the MR, and then we rotate the cycle, take the patient to the PET scanner for the second exam, and then we fuse the images together, actually present them to the MDs. This is the system actually designed by Siemens, and this is the one by GE, this is the one by United. So all those 3 systems enable simultaneous instead of sequential acquisition of PET MR, which is one of the main actually probably disadvantages of the Philips system. You obviously need to use MR compatible technologies for the readouts. So those systems, they use either avalanche photodetectors for the Siemens system or silicon PMs for the G and the United Imaging system. And those systems produce images with excellent image quality, so you can appreciate actually the PET and MR for the brain, for the cardiovascular system, so gated actually for imaging the heart. And you can basically capture the motion with dedicated protocols. And those systems actually are being used actually for research, and pretty large number of papers are in the literature today. So one of the issues, obviously, when scanning patients is what we call the respiratory motion, which tends actually to decrease the contrast and blur the lesions, especially if they are located in the abdomen or in in the thorax, as you can see for those lesions here. And to get rid of this, so people have been using respiratory gated imaging to synchronize the data and acquisition system with respiratory signal. It has been reported in literature that using simple static scans for some small lesions located in the thorax, in the upper abdomen, might be missed with static imaging and respiratory gated imaging, even if it increases the noise, which actually enables you to detect and depict those lesions. So for this purpose, we use synchronized data acquisition. So basically, synchronize the data acquisition with the respiratory cycle, and then decompose the acquired data into different respiratory phases. So we can do this for the PETs and for the CG, and engage the images. And what we can also do to improve the image quality is simply to align the different phases to reference one, and then freeze the motion. So this is a very popular area of research that have been exploited fully in few academic institutions to use actually gated for the PET-CT imaging for the radiation therapy treatment planning. And you nicely see here, so the moving lesions and how this can be actually used to guide the treatment plan so that the shape of the multileaf collimators match exactly the shape of the lesion in time and space, and enable actually to treat these patients. So the last part I have is deep learning and AI-based solutions. I don't know if I still have the time to go through these slides or have to stop here, so it's up to you to tell me. What shall I do? Stop here or just spend couple of minutes on the last slides?
Okay, you can go on with this presentation.
Okay, so just very quickly, so just AI-based solutions are being used actually in a number of applications in multimodality imaging, and the idea is that basically whatever is performed by the human can be performed by AI-based algorithms in an efficient way. And probably, so we're going to, at some point, as reported in this very nice review, published in Nature Reviews in Cancer, so the AI performance is going to reach the same level of performance achieved by humans, and even outperform it in the near future. From the same reference actually, so AI is impacting radiology in a number of ways. Basically, so affecting the workflow for the data acquisition. Obviously, the applications are going to be task based, and for the three main applications actually that I'm going to describe today is basically the detection of disease, characterization of the disease once it's detected, and this characterization could be either segmentation of the lesions from CT, PET, or MRI images to achieve better diagnosis, and can be used also for staging, for monitoring the response of treatment, and also for therapy planning and predicting the outcomes as well. So let me just go through some of the recent works carried out by our group. So this is some work that we did basically to decrease the radiation dose from the chest CT examinations of COVID-19 patients. Obviously, you know that CT scans is not the first line diagnostic exam. It's actually still PCR, but a number of countries actually who do not have easy access to this type of tests, that they still use just CT imaging. And by this, I mean countries like Iran, like Algeria, and a number of other countries in the Maghreb region. And so the idea here is that we use the units for the purpose of basically generating low dose, high dose scans or standard dose scans from low dose scans. And we generated low dose scans from the full dose scans, and then we trained the network actually using the two data sets, and you see basically the outcome here. So this is the full dose scan, so good image quality. You see the COVID-19 lesions in this area here. This is the low-dose scan, which is extremely noisy, could actually hamper the clinical diagnosis, because we basically reduce the dose of the patients, but we need also to achieve diagnostic quality CT examinations. And this is the predicted full dose scan from the low-dose scan, so using the trained network. And obviously, so it worked out very nicely on over 90 and 95% of the scans that were evaluated in this work. But we had some outliers, and I think it's only fair to report that AI-based solutions work quite well in the majority of cases, but you have outliers because it's black box solution. So the technology might fail in some cases, and we see here one such a case. This is the full dose scan, and this is low dose scan, and the predicted full dose scan had some issues actually because we saw some artifacts and the lesions were not quite well visible, so compared to the full dose scan. The second application, so this is still work in progress, not published yet, is the segmentation of the lungs and the infectious lesions. Again, a ResNet network that is used actually to, maybe you don't see the contours in well here, but you see them nicely. So this is the AI-based solution trained actually by manual contouring of the lungs and the infectious lesions that you see here in the lungs by radiologists, and these data sets were used as input actually for the training of the convolutional neural network. And you see that the artificial based solutions actually matched quite well the predictions by the network. And this is a 3D display. Again, the manual versus the predicted, and you see that the correspondence is really very good. Probably see it better in this slide here. So this is a 3D display. Radiology segmentation of the lungs and of the COVID lesions, and you see that the match between the two is really perfect, and if not excellent. Another application is the construction of computational anthropomorphic models using deep learning strategies. And obviously, so if you look at the literature, so modeling of the
Professor Habib, we can stop there?
Yeah, we can stop. Yeah, obviously I can stop here. So just to show you here very quickly, so some of these models here that have been developed, and the basically the automated segmentation achieved by the deep learning. And we use also the same type of techniques to reduce the activity injected to the patients or to the scanning of the patients. And we use this for quantitative imaging as well. So this is a way actually to generate sort of CT images from the MR, so without using the CT. So these are really extremely robust technologies. So let me just, I don't really need to summarize, probably give you some possible scenarios for the future. So we thought that PET-CT is going to disappear and leave the place for PET-MR. So obviously this didn't happen. Heated debates actually are published in the literature on this, and our colleagues MDs are still looking for killer apps actually for PET-MR technologies, and hopefully so PET-MR is going to use in the clinic in the near future. This is the members of my group, so knowledge the funding by the different funding bodies, and thank you very much for giving me the opportunity to address you today, and be happy to address and to answer any questions. Thank you very much.
Thank you, Professor Zaidi, for this wonderful presentation. Now let's move to pick up some questions from the audience or through the Q&A. I think we have one question. Thank you, Professor Zaidi. Can these techniques use in vehicle or energy industry, and why?
Well, I think the nuclear industry and obviously so for the control of different instruments, I mean, manufactured can be also made using ionizing radiation, and I think pretty large number of companies are using not really the same type of technology. Is basically for controlled checking of the equipment manufacturer, including those used actually for oil in the desert, and also for other applications. I mean, apart from medical applications.
Okay, we have another question. How we can improve the quality of X-ray images?
I mean, it depends. If you talk about radiography, so basically the idea is to improve either the spatial resolution or again, so there are different ways of improving the image quality using highly sensitive detectors. Basically, I mean, the constraint is really to be able to also to improve the image quality, but without increasing the radiation dose to the patient. For X-ray CT, I think what we have witnessed during the last decade in terms of improvements in image quality for X-ray CT is through the design of highly sensitive detectors with small focal spots to improve the spatial resolution, and especially the introduction of iterative statistical reconstruction techniques to improve the spatial resolution and image quality without increasing the radiation dose to the patient once again. Other questions?
Yeah, I have one question about breast cancer detection. What is the resolution if we combine PET with the magnetic resonance imaging to detect the thickness of the small tumors? Or in other way, what is the resolution of these techniques?
Well, basically, I mean, depending on the systems that we are talking about, if you talk about systems used in whole body imaging, I mean, the spatial resolution that can be achieved in PET is at best 3 millimeters, I mean, for whole body imaging. And then for MRI, obviously, the spatial resolution is very high. I mean, the issue is that for some type of malignant lesions, so some of them, they show up only on the PET images, and they do not show up on the MR images. I mean, despite the high spatial resolution, and so the spatial resolution is not the only issue that we need to talk about, because even if the spatial resolution is not very good in the case of PET, I mean, the molecular sensitivity is extremely high, and I've shown some examples actually where even for very small lesions, even below the spatial resolution of clinical PET systems, so those lesions can be detected as well.
Okay, thank you. Another question is about training the network with images of COVID-19 patients. Is there enough data?
Well, actually, so one of my colleagues, actually, we got about 10,000 chest CT images that we are using in our research. So these are not in the public domain. We're not allowed to share them yet, but the University of Chicago, they got actually, I think, $20 million to build a pretty large database for COVID-19 chest CT scans, and they are going to be in the public domain for clinical research. I think these are some of the pretty large databases. China, I think I've seen papers with 5,000, 8,000 studies, and that this is obviously more than enough to train the networks.
Okay.